Great. All right. So to follow on from the introduction earlier then, aims of the talk really are in sort of three parts. So the first part is just to tell you a little bit about our flood mapping and how we go about doing that so that you can get a sense for how we produce these maps. The next part is all about how we've used free and open source software, like GDAL as mentioned earlier, to automate some of our processes and improve the efficiency with which we can create these flood maps. Then the final section is our latest bit, and this is new for us as a company, but this is about how we're pushing out cloud services using serverless approaches. Okay. So we've got a picture here of the offices, which are over in the Broughton Hall estate near Skipton, nestled in the edge of the Yorkshire Dales there. So JBA Risk Management itself, we're a data provider. We provide flood risk data and flood risk models as well. And we've got about 120 staff, and it ranges from software developers and data scientists and hydrologists. We've got a few smaller offices dotted around the world as well. So that's what we look like. And core of the business is our flood maps. So this is what the business was built upon. And in the preparation of flood maps, there's a gold standard. The gold standard is hydraulic models, okay, so hydrodynamic simulations. And what these involve is you get a digital elevation model and you parameterize it with some runoff coefficients, that kind of thing. And then you put some water on the map, either simulating rain or flows into rivers. And you then run a simulation. And the simulation is solving these shallow water equations. I'm not going to go into those right now. And you run a time series and watch how the water flows down the hillsides, down the rivers. And once the simulation is complete, the bit we're interested in is the maximum that the flood gets to. Now, these shallow water equations, they're computationally quite expensive. It's one of the reasons that, well, there's a number of other ways you can produce flood maps. This is the best, but also slow. So the big innovation that was the reason for the creation of JBA Risk Management in the first place was that you could put these hydraulic models onto GPUs, okay? And that was late 2000s, sometime around 2007, 2008. A nice technical innovation demonstrated that you could speed up these simulations by something in the order of about 1,000 times. And that opened possibilities. It's a nice example of how a technical innovation kind of leads to, creation of the company, essentially. So just a little bit about the flood types themselves. What we've got on the map here, there's a couple of different flood types that I'm going to explain here, shown on this map. The first is surface water flooding, otherwise known as flash flooding. What happens here is it rains on a hillside or anywhere for that matter, and the water flows towards the rivers in a heavy rainstorm that can cause flash floods as the water is on its way to the rivers, and it can happen, virtually anywhere really. And the second type of flooding is river flooding. That's where the rivers swell, too much water in them, they burst their banks and flood the valley. So they're the two main flood types. And the other one we deal with, that I'll mention here as well, is the coastal storm surge. And this is where, in a storm, you'll get the surge of waves breaching defences, the water goes into the city. So those are the three main flood types that we model and that we produce maps for. And so as mentioned before, that technical innovation of running hydraulic simulations on a GPU allowed the people who founded the company to produce the first national scale flood map. They did this in 2007. So this is a 5-meter resolution map. So what you can see just about here is that, well, we've got a bit of coastal flooding coming up the Humber. There's purple dots around, which is the surface water flooding, and then in the blue, the river flooding, where the rivers are bursting the banks. And yeah, this flood map we've been maintaining every year since. It forms the basis, well, address cloud base some of their products on it too. Okay. So that was the early days, and so in the early days when producing these maps, it was done with GIS analysts using desktop software, typically using ArcGIS as well. And I mean, that worked well. It was what produced the UK flood maps and most of the global maps that I'll show you in a moment as well. But it didn't scale particularly well. So there's a lot of manual processing, clicking through routines, and when the maps got bigger, then these desktop tools struggled with it. So a few years back, we started investigating a different approach, and that different approach was based on GDAL. So we produced a toolkit internally it's called the FARM toolkit. FARM is the Flood Analysis, Report and Management. One of those acronyms that I think was sort of mostly so it came up with a nice name. So, and this toolkit, we've been developing it at JBA since about 2016, and it's a number of freestanding modules for doing different, largely GIS, but any kind of processing really. It's accessible as command line tools, also as Python functions as well. And as mentioned before, because a lot of our data is spatial, GDAL provides that spatial engine. And so a couple of examples here, one fairly simple one on the left, which is probably our most used function. This is the zonal statistics function. Essentially, you've got a polygon, fired in a raster, and it derives some flood statistics in a particular way. Okay, so that's a fairly simple one. Some of them are more complex. For example, the one on the right is another piece of work we did, which that uses neural networks and detects river defenses, raised river defenses. So they range in complexity really, but all of them are freestanding and usable on their own. All right. I didn't expect an animation there, but the other thing that we've done with this is strung all these farm components to form automated workflows. These largely run internally, but we've used Django with a system called Celery for asynchronous task execution, all based on PostgreSQL, and that allows us to do these automated processing that well, makes us much more efficient, essentially. So the one shown on the right there, we're running those those hydraulic simulations in a bunch of catchments for different flood types, for different likelihoods of severity, and these are being run and then an automated workflow merges them all together, does some QC checks, fixes a few issues, sends a few back, and the whole thing cycles around and produces our flood maps. And this is how we're going about producing and updating our flood maps these days. And in fact, most of this was done before we moved to the open source, but this shows our global flood maps. The original release in 2016, we have 30-meter resolution everywhere, all produced with the hydrodynamic modeling approach. We've got the 3 flood types I mentioned earlier, and we have a range of different bands of information, so a number of different return periods for each flood type. And in total, it's about 250 countries with quite a number of bands of information in each raster. And just to give you a sense of the scale as well, that's if you merge the whole thing together, which we do have, it's about 1.3 million by 570,000 pixels at the 30-meter resolution. So it's quite big. There's quite a lot of data there. And we have since moved on to more 5-meter resolution maps. The latest one is the US, and again, that's a similar size to the globe at 30-meter resolution. We've got the 3 different flood types that I mentioned earlier, but we also have 5-meter resolution in Europe and Australian cities too. So those are the data sets that we work with. The traditional model is one of a data provider. So we provide these rasters to insurance clients and reinsurance clients. And we also do analytics on them and produce data sets that we can send to our clients too. So the next step then was, as mentioned before, new to us, that was moving towards data service provision using cloud computing. So in the UK, we've produced this data set for more than 10 years now. And what we would do is we would take location information, say OS Open UPRNs or GeoPlan, and we run those locations across our maps and pre-calculate the flood risk for every property or postcode in the UK. And we have different representations of flood risk suitable for different end users. So floodability was a simple traffic light system. It's used by a lot of insurance companies. Green, fine, red, at risk of flooding. We also have flood scores, which provide a little bit more quantitative information of the flood risk, and we have more sophisticated calculations that allow you to calculate the cost of flood insurance for different property types. And so each time we produced a map update, we reproduce its data set and ship it to our clients. That's all well and good. It's worked well for us. However, it's a little bit flawed as well, and that's that it's not particularly flexible. Now, the first problem is that most countries in the world don't have those exhaustive property locations. And the second one is that it's not particularly flexible. There's many cases where the person interested in the property might know a little bit more about it. They might know that actually an outbuilding is particularly important or something like that, or a caravan park. And so when we pre-calculate, there's no flexibility to change the property boundaries as well. So something more dynamic would be helpful. And the approach that we took to this was essentially outlined by Tom a few years back at Prosper G conference. And for anyone interested in this approach, I'd recommend checking this presentation. But he outlined an approach using Cloud Optimised Geotiffs that were held on S3 using serverless landers, and that provided a neat solution to what we were looking at. Okay, so this is building on that idea and adding in some more of our calculations. So a couple of words on serverless. I'm sure that most people in the room are fairly familiar with it. It's been cited as the second phase of cloud computing. It's neat. There's a lot of things, benefits, particularly to data providers like us. We don't have to think about hardware and maintain data centers and operating systems and that kind of thing. It has an amazing ability to scale up, and that's something that I can show you some data for. So you can go from a single lambda to 1,000 very easily. And because the whole thing switches off when you're not using it, when the API is not being accessed, you can completely switch off the system. It's potentially more cost and environmentally efficient too, which is great. So here's a core function for us. Okay, so it's going back to that zonal stats function I mentioned before. We're taking an input polygon. We're using the AWS serverless toolkit. It runs through the API gateway, which is helps organize all the APIs. We've then wrapped up our farm function, the zonal stats function, in a lambda, which is a serverless cloud function. And all of our data sets are held in Geotiffs, Cloud Optimised Geotiffs on S3. So the polygon is applied to the API. The zonal stats function coordinates things and sends a bunch of requests to look up the data in the rasters. The data in the rasters is returned, processed by the zonal stats function, and sent back. And what you get back is a bunch of flood depth statistics. Okay, for the different flood types, for the different severities, and information about river defences and that kind of thing. And this works quickly and efficiently too. Okay. So in terms of how we've structured the API, you can hit single locations with a GET request. You can send batches of locations and calculate, say, 100 points at a time. and that improves some of the efficiency for running through very large data sets. And so, to give some information on performance and scaling here, this was a data set that we set up just to try things out. This is 100,000 random points in France that we were applying to the API to look up the flood risk. It was 10 meter upload against the 5 meter resolution map. My preferred way of interfacing with the API is to use a command line tool that we've set up. So that allows you just to give it a file full of points. It sends it to the API, scales it by 100 simultaneous requests, and you get a file of your results back at the other end. And running through those 100,000 points with a cold start takes about 2 minutes. So the throughput is very good. And in fact, if you take it above 100, you can take it up to, we've tried up to 1,000, and it gets quite a lot quicker than that. It's about 1.5 minutes for a warm start with 100 simultaneous requests too. So that zonal stats function forms the core of our calculation. And so what we've then done is added more of the farm calculations that we use to prepare our data sets as additional lambdas here, and provided a number of API endpoints to access those. So for any point or polygon globally, you can calculate the floodability, the traffic light scores, or the flood risk scores, or the cost of flood insurance using some of our calculations. And further to this, an emerging area in the insurance market is around climate change. And just to demonstrate how we're incorporating climate change models into these calculations too. What this slide shows, again, we've got a point or polygon sent to the API. We get our flood risk statistics from the geotiffs on S3. We can then incorporate some climate scenario information, adjust the flood risk, and then calculate floodability or flood scores or pricing data, those risk representations for any climate change scenario that we've modeled. So on the chart on the right there, that shows France, those 100,000 points. The areas in red are where in the future scenario, 2066 to 2095, a climate scenario, red is where the flood risk is going up. And blue in the south of France is where things are getting drier and the flood risk is going down. And so this flexibility allows people to, well, basically calculate flood risk according to their requirements. So that's it. We have a quick summary. We've used an approach outlined by Tom for the previous FOSS2G event to use Cloud Optimised Geotiffs hosted on S3 and GDAL to do fast lookups against rasters. It allows us to do on-the-fly calculation of flood risk for any location globally. The scaling means that we can do very fast batch calculations, and it gives that flexibility that we're looking for. So it's a model that we're continuing to explore there. That's it then. Thank you.
I'll charge for that technical advice.
Could we be later on? Okay.
Question?
Probably for you. How do you get around the lambda payload but it doesn't hang up? Let's say 2 minutes, but the lambda should get and return, it hangs up. How do you get around that? But the lambda does the batch process and doesn't hang up and receives 100,000 or 1 million points because of the 5 megabyte payload of the lambda.
Well, the way that we do it is not to have one payload go through one lambda. To have something in front of that, then splitting that job into multiple lambdas.
Oh, that's the API gateway, that's what it does.
Yeah, potentially. It depends on how you set your batch up. Maybe if you're doing it on what our client tool does, it's a bit weird. What we do is say, I've got like 1,000 locations to look up, so I'll send them in batches on the client, or we've also got some tests to use what's called a step function, which is basically flow chart for lambda functions. where you can say, I want a long running job. You can parallelize within that. And that job could be like, I've got a database table, I've got an S3 file, an S3, so that's something that we do, actually not for JBA work, but for processing large batches for flood reinsurance in this country. So yeah, I could just talk about more offline, but that's how you can basically, there are tools to allow you to orchestrate, say, not just one, but the scale is lambdas to handle that job in parallel.
And so far, the approach we've taken is just to limit the batch to 100 requests, and those return typically in a few seconds. And so we haven't breached any timeout limits yet.
Okay. So you do command line, you're interesting in batches then?
Yeah. The onus on the client to break into batches and do it sensibly.
That's great. I could have loads of questions later in the pub, but in the meantime, so obviously at the moment, the way JBA provide their data historically has been a kind of a big annual refresh of the map. So does the API allow you to kind of like, I don't know, so now we're, the map's not out for another few weeks, but would this go against the latest data, or it's always against the version, the latest published version?
So by default, it's the latest published version. So when we're ready to release the map, we'll push it to the server at the same time, to S3. We've provisioned for previous version access, so we don't remove any of the older versions. And so it's possible to run against last year's data, for instance.
That's great. And can't remember. That's fine. I'll think of it later.
Yeah, sure.
Oh, it's just I guess a kind of commercial thing actually was. So is it accessible? Is there a cost for the service? Is it accessible, or kind of like any basically licensed customer of JBA be able to use the API?
That's the kind of thing you can raise tomorrow, potentially. But I would hope that in your case particularly, it would be done favourably. There are costs to us, and we are seeing this as a commercial product too.
Great, thank you.
Just on the SDK there, you mentioned it, so I guess your command line tool, a bit of batching and all that. Do you provide that to clients an SDK or a tool, or is it just, here's the API and the docs?
This is all new stuff for us, is the first thing to say. But in principle, we can put that command line tool on PyPy if we want. We've got it on GitLab at the moment, and so it can be installed with a pip. And as long as they've got the credentials to access the data, then it means that you can use it to.
I've got questions in the pub later as well.
All right.
Brilliant. Thanks so much, Dave.